Welcome to this lecture on sequences and series of functions. Today, we are exploring a fascinating and fundamental question in advanced calculus. When are we allowed to swap a limit and an integral? This might seem like a simple algebraic trick, but as we will see, it requires careful mathematical justification to avoid impossible contradictions. Before we dive into the equations, let us understand why this concept matters. Imagine you are managing a construction site, building a massive dirt hill. You can measure the volume of dirt added every single day and see what final number that trend approaches. Or you could simply wait until the very end of the project and measure the final completed volume. In everyday life, common sense tells us both methods give the exact same answer. In mathematics, we have a sequence of functions that approach a final limit function, and we want to know if the limit of their areas equals the area of their final limit. This brings us to a critical realization. In everyday life, the two methods match perfectly. But in the strange and infinite world of mathematics, they do not always agree. To safely swap the limit and the integral, we need a strict, non-negotiable condition called uniform convergence. Uniform convergence means that the sequence of functions approaches the final limit function at a consistent, guaranteed speed across the entire interval. It ensures the curves lock into their final shape evenly everywhere at once, without any wild, unpredictable spikes that could hide extra area. Now that we understand the requirement, here is the mathematical representation of the interchange theorem. The expression on the far left represents taking the integral, or the area, of the sequence first, and then finding the limit of those area values. The expression on the far right represents finding the limit function first and then calculating its integral. The middle shows the actual interchange step, moving the limit inside the integral sign. This swap is perfectly legal, and the two outer expressions are exactly equal, as long as the sequence converges uniformly to the limit function. If this condition is met, you can choose whichever calculation is easier. Before we prove the theorem, let us see this with a concrete example where the interchange works perfectly. We are given a sequence of functions defined as x divided by n on the interval from 0 to 1. Our goal is to see if the limit of the integrals matches the integral of the limit. First, we find the limit function. As the denominator n grows infinitely large, the fraction shrinks to 0 for any value of x. So our final limit function is just a flat horizontal line at 0. Integrating this flat line of 0 simply gives us an area of 0. Continuing with our example, we will now test the second path to see if it matches. We will calculate the integral of the sequence first, while n is still a finite number, to find a general formula for the area at any given step. Since n is just a constant number with respect to the variable x, we can pull 1 over n out of the integral. Then, we just use the standard power rule of calculus to integrate x, which becomes x squared over 2. Evaluating this from 0 to 1 gives us the sequence of the areas, which is exactly 1 over 2n. To finish this problem, we now take the limit of this area sequence as n approaches infinity. As n gets infinitely large, the fraction 1 over 2n shrinks exactly to 0. What does this mean physically? It means both calculation paths led to the exact same destination. The limit of the integrals is 0 and the integral of the limit is also 0. This proves that the interchange was successful and mathematically valid, exactly as the theorem promised, because the sequence was uniformly convergent. So, we have successfully used the formula, and now we must understand exactly why it works by deriving the theorem. In mathematics, proving that two things are equal is often done by proving that the absolute difference between them shrinks to exactly 0. Therefore, we start by looking at the absolute difference between the integral of the sequence and the integral of the final limit function. Using a fundamental property of integrals, we can combine these two integrals into a single expression and then move the absolute value bars inside the integral sign. This represents the vertical distance between the sequence curve and the final limit curve. Continuing our derivation, this is the crucial moment where uniform convergence saves the day. Because we are given that the sequence converges uniformly, we have a massive advantage. It guarantees that for any tiny positive number we choose, which we call epsilon, the vertical distance between the curves is strictly bounded. We can trap the entire curve within a tiny distance of epsilon divided by the interval width, b minus a. This single inequality holds true for every single point simultaneously. We can now substitute this guaranteed maximum height difference back into our integral inequality to find the maximum possible difference in their areas. This brings us to the final result of our derivation. By replacing the actual distance with its guaranteed maximum value, we create an integral that is incredibly easy to solve. We are now just integrating a constant number. Integrating a constant simply means multiplying that constant height by the width of the base, which is b minus a. The width terms perfectly cancel out, leaving us with just epsilon. Since epsilon can be any tiny number we want, the difference between the two areas must be shrinking exactly to zero. Therefore, the limit of the integrals is perfectly equal to the integral of the limit. Now that we have proven the theorem, let us look at a diagram that visually explains the core engine of that proof. Because the sequence converges uniformly, the entire dashed curve is eventually forced to live inside a very narrow epsilon tube surrounding the final solid limit function. Since the curve cannot escape this tube at any point, the total area under the dashed curve is strictly locked in. It cannot suddenly grow massive or shrink to zero, guaranteeing a safe convergence. We have seen when the interchange works, but now we must look at a dangerous example where the interchange completely fails. This highlights exactly why uniform convergence is so strictly required. Imagine a sequence of functions that forms a moving, shrinking tent. For any step n, the function forms a triangle with a tiny base and a massive peak height. Outside of this base, the function is 0. As the steps progress, the tent gets taller and taller, but its base gets narrower and narrower, sliding towards 0. Let us see what happens if we try to swap the limit and the integral for this shrinking tent. First, we calculate the area of this triangular tent at any given step n. Using basic geometry, the base is 2 over n and the height is n. When we multiply them together with the 1/2 from the triangle area formula, the n variables completely cancel out. This means the area under the curve is exactly 1 for every single step in the sequence. So the limit of these areas is simply 1. Continuing with our shrinking tent, we must now look at the limit function itself. What happens to the actual shape of the curve as n goes to infinity? If you pick any specific point on the graph, eventually the shrinking base of the tent will slide completely past your point. Once that happens, the function's value at your point becomes exactly 0 and stays 0 forever. Therefore, the final limit function is completely flat. The tent has vanished into thin air, leaving a value of 0 everywhere. This brings us to a massive contradiction. When we integrate this completely flat final limit function, the area under a flat line at 0 is of course 0. But wait, we just proved in the previous steps that the limit of the areas was exactly 1. 1 does not equal 0, meaning the interchange has completely failed. Why? Because the convergence was not uniform. A rogue wave carried an area of 1 all the way to infinity, tricking the limit of the integrals, while the pointwise limit function missed it entirely. To summarize our lecture, the interchange of limit and integral is a powerful tool for simplifying impossible calculations in advanced engineering and probability. However, this swap is only mathematically legal if the sequence of functions exhibits uniform convergence. If they only converge pointwise, rogue spikes can hide area, causing the two calculation methods to yield completely contradictory results. Always verify uniform convergence before swapping.